Complex numbers have useful and important applications in science and engineering, and many of us would have been introduced to complex numbers pretty much in high school. In this video, I'm going to talk about an operation of complex numbers, which is multiplication and division, and in particular, I'm going to focus on the geometric representation or interpretation of multiplying or dividing two complex numbers. So typically, the general form of a complex number is something like x plus jy, where x is the real part of the complex number and y is called as the imaginary part of the complex number, and j is the imaginary number, which is the square root of -1. So where j equals square root of -1. So let's take a couple of complex numbers and perform multiplication between those complex numbers, and we will see what happens as a result of that multiplication when we represent those complex numbers geometrically in the complex plane. So let's take an example of a complex number such as 1 plus 2j. So we have the real part as 1 and the imaginary part of this complex number is 2, and let's multiply that with another complex number, and let's take that as 2 plus 1j. So the real part of the second complex number is 2 and the imaginary part is 1. It's 1j, right? So we have these two complex numbers and we can multiply these by the usual rules of multiplication using the distributive property. So we get it as 2 plus 2j, j plus, we'll have it as 4j plus 2j squared. So since j is square root of -1, it implies that j square is equal to -1. So we'll use that fact over here. So that makes it as 2 plus 5j plus 2 into -1. So that becomes 0 plus 5j, which is simply equal to 5j. So that is basically the product of these two complex numbers happens to be a complex number where the real part is 0 and the imaginary part is 5. So since the real part is 0, we write this as simply 5j. So that means this complex number is purely imaginary. Now, to understand the geometric representation of this product, we need to do a couple of more computations, and those are, we'll need to compute the magnitude of the first complex number and the magnitude of the second complex number, and also we need to find the angles of these two complex numbers. So the magnitude of the first complex number, 1 plus 2j, will be 1 plus 2j magnitude. That denotes magnitude. That is, the general rule for magnitude is the square root of the real part squared plus the imaginary part squared. So that's 1 square plus 2 squared, which is equal to square root of 5. So that's the magnitude of the first complex number. The magnitude of the second one is magnitude 2 plus j, which will be again square root of 2 square plus 1 squared, which is equal to again square root of 5. So we have the magnitudes of these two complex numbers as square root of 5, and we can also calculate the angles of these. So the angle of 1 plus 2j is the arctangent or the tan inverse of the imaginary part by the real part. For the first one, it's 2 by 1, excuse me, which is tan inverse of 2, and that is equal to 63.43 degrees. 63.43 2.43 degrees. Okay, I'm writing these angles in degrees. Similarly, the angle of the second complex number 2 plus j will be the arctangent, tan inverse of the imaginary part by the real part, which is equal to 26.57 degrees. So we have all the information we need to understand what happens when two complex numbers are multiplied. So the way I'm going to represent this is what happens when this complex number 1 plus 2j is multiplied by another complex number 2 plus j. So 1 plus 2j has a magnitude equal to root 5, and 1 plus 2j has an angle equal to 63.43 degrees. So we want to see what happens to these magnitude and angle of the complex number 1 plus 2j when it is multiplied by another complex number 2 plus j, which has a certain magnitude and a certain angle. So let's look at these complex numbers geometrically in the represented in the complex plane, where we have the real part represented on the x-axis and the imaginary part represented on the y-axis. So we have a two-dimensional complex plane on which we can represent these complex numbers as points, and we will see that we will be joining these points to the origin to obtain them as vectors having a certain length, which is the magnitude, and a certain angle with the positive x-axis. So with the x-axis representing the real part and the y-axis representing the imaginary parts of these complex numbers, so we have this two-dimensional complex plane. So the first complex number 1 plus 2j has a real part equal to 1 and the imaginary part equal to 2. So it can be represented as 1 comma 2. So it's 1 on the real axis and 2 on the imaginary axis. So it corresponds to this point over here and denoted by this red line. Okay, the point 1 comma 2 connected to the origin by this red line, and this red point is the representation of the complex number 1 plus 2j in the complex plane. So that is basically 1 comma 2 is our point in the complex plane. And the second complex number is given by this green dot, which is 2 plus j. So it has the real part equal to 2 and the imaginary part is 1. So 2 plus j corresponds to the point 2 comma 1 in this complex plane. Now what we see is that after multiplying these two complex numbers, the result that we get is 0 plus 5j, where the real part is 0 and the imaginary part is 5. So that corresponds to 0 comma 5, so 0 on the x-axis and 5 on the y-axis. So it corresponds to this blue dot over here. So 0 comma 5 is denoted by this point in blue. So that's representing the complex number, which is the product of the two complex numbers that we chose, 1 plus 2j and 2 plus j. Now, each of these complex numbers has a certain magnitude and a certain angle. So 1 plus 2j has a magnitude of square root of 5. So this length of this red line from the origin to the point 1 comma 2 is having a length of 0.5. And we can compute that we're using the Pythagoras theorem, which is exactly what is being done here. 1 square plus 2 square is under the root is square root of 5. So this is having a magnitude of root 5. Similarly, the distance of the second point 2 comma 1 from the origin is also square root of 5. Now the angle that the first complex number 1 plus 2j makes with the positive real axis, that is equal to 63.43 degrees. So I'm going to mark that here. So that angle here is 63.43 degrees. And the angle that the second complex number 2 plus j makes with the positive real axis is 26.57. So That's 26.57. Now what we notice here is that when we multiply the complex number 1 plus 2j with another complex number 2 plus j, the resulting complex number which we got is 0 plus 5j. This result, we can notice or we can observe that there are two effects that have taken place as a result of multiplying the complex number 1 plus 2j with 2 plus j. One of the things that has happened is because of this multiplication, the result that you have got has got a change in its length. So this is a longer line. It could be shorter also, but in this particular case we see that the length of this line after multiplication has changed. So there is a scaling effect. And the other aspect that we notice here is that there is a rotation that has happened. So initially this complex number is having a certain angle which is 63.43 degrees with a positive real axis, but after multiplication, the result that we got, that complex number is having an angle of 90 degrees in this case with the positive real axis. So there are two things that have happened as a result of this multiplication. One is scaling and the second is rotation. So let's write those down. So scaling and rotation. So this is the first piece of information that we observe when we multiply two complex numbers, and that goes to dividing as well. So the process of multiplication produces two changes in the complex number. One is its length gets scaled, and the second one is the complex number or the vector denoting that complex number gets rotated depending on the scaling, and the rotation depends on the complex number with which it is being multiplied with. So these are the two effects that happen as a result of multiplying a complex number with another complex number. Now let us elaborate this further by having a larger representation of this diagram so we can work out things more clearly. So here we have the same diagram where it's shown slightly bigger. So we have this complex number which is 1 comma 2 denoting 1 plus 2j, and this is 2 comma 1 denoting 2 plus j. So we are multiplying 1 plus 2j with 2 plus j. So that's what we have been doing. 1 plus 2j is being multiplied with 2 plus j to get the result 5j, which is nothing but 0 plus 5j. Right? So 1 plus 2j is having a certain angle with the positive real axis, and that angle is equal to 63.43 degrees. The angle of the second complex number with the positive real axis is 26.57 degrees. Okay, and the magnitudes of both are root 5. So the length of this is square root of 5, and so is the length of this. It is square root of 5. So we have these complex numbers. Now after multiplying 1 plus 2j with 2 plus j, two things happen. The magnitude of 1 plus 2j gets scaled by the magnitude of the other complex number with which it is getting multiplied. Since the magnitude of 1 plus 2j is root 5, it will be scaled by the magnitude of the second complex number, which in this case is also equal to root 5. So the magnitude of the product is going to be the product of the individual magnitudes. So let's write down the magnitude of 0 plus 5j is square root of 0 square plus 5 square, which is basically equal to 5. So the magnitude of this product is 5. So that means it has a length of 5. Clearly, it has a length of 5 from 0 to 5. So, and this 5 is basically the original complex number, the 1 plus 2j, getting scaled, or its magnitude being scaled by the magnitude of the second complex number. So clearly we see that the magnitude of the product is equal to the product of the magnitudes of these two complex numbers. So root phi into root phi gives us phi. So the magnitude of the first complex number is root phi, the magnitude of the second complex number is also root phi, and the magnitude of the product is root phi into root phi, which is phi, which is what we get exactly here. Okay, so the scaling is happening in such a way that when we multiply a complex number with another complex number, the magnitude of the first complex number gets scaled by a factor equal to the magnitude of the second complex number, which gives us the magnitude of the product of these two complex numbers, so which is what we see here. Now let's see what happens to the angles in terms of the rotation. The second effect that takes place is rotation. So let's see what is the amount of rotation that takes place when we multiply two complex numbers. So let's look at the angles now. The angle 1 plus 2j makes with the positive real axis is 63.43 degrees, and the angle 2 plus j makes with the positive real axis is 26.57. Now when multiplying 1 plus 2j with 2 plus j, the effect that is going to happen is a rotation of 1 plus 2j by an angle equal to the angle that 2 plus j makes with the positive real axis, and that rotation will be in the counterclockwise direction. So this 1 plus 2j is going to be rotated in this direction by an angle equal to the angle that 2 plus j makes with the positive real axis. So the resulting product that we have here will have an angle equal to the angle that 1 plus 2j makes with the positive real axis plus the angle that 2 plus j makes with the positive real axis. So the total angle for the product will be 63.43 degrees plus 26.57 degrees, which is exactly equal to 90 degrees, and that is exactly the angle that we have got for the product vector or the product complex number, which is 0 plus 5j. So we see that as a result of multiplying a complex number with another complex number, the first complex number gets rotated counterclockwise by an angle that is equal to the angle that the second complex number makes with the positive real axis. Okay, so combining these two properties, which is the scaling property and the rotation property, we see that the effect of multiplying two complex numbers is that the magnitude of the first complex number gets scaled by the magnitude of the second complex number to which it is being multiplied with. And the second effect is that a rotation of the vector representing that complex number happens in the counterclockwise direction, where the amount of rotation is equal to the angle that the second complex number makes with the positive real axis. So that's what we observe here. So a common operation of complex numbers, which we are all familiar with, but we hardly notice this geometric interpretation. And that is the objective of this video, to bring out this geometric interpretation of what happens when two complex numbers are multiplied. Now, since the multiplication operation is commutative, that is changing the order of the multiplication, it does not change the result. So multiplying one with the other is the same as multiplying the second with the first. So rather than saying 1 plus 2j gets scaled by the magnitude of 2 plus j, we could also say that 2 plus j gets scaled by the magnitude of 1 plus 2j as a result of multiplication. And similarly for the rotation part, rather than saying that 1 plus 2j gets rotated by an angle made by 2 plus j, we could say that 2 plus j gets rotated counterclockwise by an angle made by 1 plus 2j with the positive real axis. And that follows from the commutative property of the multiplication operation. Okay, so that gives us a clear picture of what is the geometric interpretation of multiplying two complex numbers. Now, another important analogy or similarity that we're going to see here is that because we are representing these complex numbers as two-dimensional vectors, we have to recall from our linear algebra background that multiplying a vector with a matrix also has a similar effect of scaling and rotation. So we will try to establish the analogy and the relationship between the complex number multiplication and the vector multiplication with its counterpart matrix, which will produce the same kind of scaling and rotation. And we'll try to make this relationship. So let us now establish the analogy with linear algebra, where we can have a vector being multiplied with a matrix, and it will this multiplication with the matrix, which is a linear transformation operator. The matrix represents linear transformation, and that linear transformation will have the effect of scaling as well as rotation. So basically what we're saying is, if we have this vector 1 comma 2, let me write that in vector form 1 2. If it's multiplied with a 2 by 2 matrix, so we don't know what are those four elements here, we need to figure it out, and that would give us the same resulting output vector 0 comma 5, which we have as a result of multiplying 1 plus 2j with 2 plus j in the complex domain, right? In terms of the complex number multiplication. But in terms of linear algebra, if we multiply this vector 1 2 with a two-dimensional matrix, we should get the resulting 0 comma 5 point here, or the vector 0 5. That means this matrix, which denotes a linear transformation, produces the effect of scaling and scaling and rotation. Now we need to figure out what would be the elements of this matrix. So what are the contents of this matrix? What do the rows and columns of this matrix represent? And we will see that these elements of this matrix, which produces the same scaling and rotation as this complex number 2 plus j, this matrix is related to this 2 plus j complex number. And what we see is that the rows of this matrix, if I can call this as a matrix, let's call it as a matrix A. Okay, this is the matrix A, the linear transformation matrix. This matrix has the form A equals, and I'll call this as the complex number B. So there is a one-to-one relationship between this matrix A and the complex number B, which produce the scaling and rotation that this matrix must produce. So obviously there has to be something, because this matrix is going to produce the same scaling and the same rotation as produced by this complex number B. So the first column of this transformation matrix happens to be denoted by the complex conjugate of the complex number B. So we denote that as B star, which is a complex conjugate of B. So if B equals 2 plus j, then the complex conjugate of B will be 2 minus j. Right? The imaginary part has its sign reversed in the conjugate. And the second column of the transformation matrix A is I times B star, or as we have been writing, J times B star, because we are writing J for the imaginary number. So it will be J times B star. So if B star is 2 minus j, the complex conjugate of B is 2 minus j, then j times the complex conjugate of B will be j into 2 minus j, which will become 2j minus j square, and since j square is minus 1, minus of minus 1 will become 1 plus 2j. So basically it is basically reversing the real and imaginary parts. So j b star is nothing but the complex number b with its real and imaginary parts swapped with each other. So that is what is going to happen here. So each column of the transformation matrix A is given by the real and imaginary parts of b star and j times b star. So that is going to be b star is 2 minus j, so the real part is 2 and the imaginary part is minus 1. So we'll have it as 2 and minus 1. And the second column of the matrix A is the real and imaginary parts of the complex number j times b star, which is 1 plus 2j. So the real part is 1 and the imaginary part is 2. So we'll have it as 1 and 2 as the elements of the second column of this matrix A. Now when we multiply the vector 1 comma 2 1 2 with this matrix A, we will get this same resulting vector 0 5. So let's perform and verify this calculation. So we have our vector 1 2 multiplied with this matrix which is having 2 minus 1 and 1 2 as its elements. So 2 minus 1 is the first column, which is b star, and 1 2 is j times b star. So when we multiply this using the normal rules of vector multiplication with the matrix, we'll get it as 1 into 2, 1 times 2 plus 2 times minus 1. So that will be 2 minus 2, which is 0. So we'll get that as 0. And multiplying this with the second column, 1 times 1 plus 2 times 2 will be 1 plus 4, which will be 5. So which is exactly the result that we had when we multiplied the complex numbers. So when we multiplied 1 plus 2j with 2 plus j, we got 0 plus 5j. So let me make that parallel over here. 1 plus 2j multiplied with 2 plus j gave us 0 plus 5j. And in vector terms, multiplying 1 2, the vector 1 comma 2 with this matrix gives us the same 0 comma 5 in the vector notation. So clearly this matrix A and this vector this complex number 2 plus j have a relationship, right? Have a connection between them, and that connection, if I call this as the complex number B, so there is some relationship between these because they are performing the same linear transformation. They are scaling the vector 1 comma 2 or the complex number 1 plus 2j and rotating it in a certain direction, and the amount of scaling and the amount and direction of rotation in both the cases is the same. So we see that this matrix A has as its elements which are related to this complex number that we are multiplying to this first complex number. So the first column of this matrix is the real and imaginary parts of the complex conjugate of this B, and the second column denotes the real and imaginary parts of the complex conjugate of B multiplied with J. Basically what we're saying is this column denotes the real and imaginary parts swapped with each other. So the real part, which is 2 here, is swapped with the imaginary part, which is 1. So 1 and 2 get swapped. So we have this as 1 and 2. Okay. So that is the relationship between the complex number and the matrix in linear algebra, which also produces scaling and rotation of the vectors with which it is multiplying, right? And obviously, for the matrix case, this idea can be extended to more than 2 dimensions as well. We can extend this to with a 3-dimensional vector multiplied with a 3 by 3 matrix, or a 4-dimensional vector multiplied with a 4 by 4 matrix, and so on and so forth. And we can extend it to any number of dimensions, but with the complex numbers, we are restricted only to 2-dimensional, because complex numbers work only for 2 dimensions, because we have the complex plane, which is represented by the real axis on the x-axis and the imaginary axis on the y-axis. So it is restricted to only 2-dimensional operations, whereas the matrices can be extended to multiple dimensions beyond the 2-dimensional plane as well. So we now see that the linear transformation of scaling and rotation is produced by when we multiply a complex number with another complex number, and we have also seen how what is the relationship between the linear transforming matrix A and the complex number B, which produces the same type of scaling and rotation. So to summarize, this matrix A is given by the columns which is B star and J times B star, where B star is the complex conjugate of the complex number B. Now, just as multiplying two complex numbers produces a scaling and rotation in the counterclockwise direction, dividing a complex number with another complex number will also produce a scaling and rotation, but in the opposite direction. So, for example, if the magnitude of this complex number is scaled up as a result of multiplying with the second complex number, then the division process will scale it back down, and when it's rotated in the counterclockwise direction as a result of multiplication, division will cause a rotation in the opposite direction, which is the clockwise direction. So multiplying, so let's call this first complex number as small a, and multiplying the complex number small a with the complex number small b produces a third complex number, which let's call it as c. And if we happen to divide c by b, it should give us back a. So c divided by b will give us back a. So from c we are able to get back a. So if we look back at the geometric representation, it should give us some more clarity. So basically what we're saying here is that the vector c is this complex number, that's c, and 2 plus j is our b. So if we can call this as b, and c by b should give us back a. So what we notice is that when we divide c by b, it gets scaled by a factor equal to the magnitude of b. So c has a magnitude of 5 and b has a magnitude of root 5, and since we are dividing, the magnitude of a should be 5 divided by root 5, which is root 5. And similarly, in terms of the rotation, when we divide c by b, c, which is having an angle of 90 degrees with the positive real axis, and b is having an angle of 23.67 degrees. So as a result of this division, c will get rotated in the clockwise direction by an angle equal to the angle that b makes with the positive real axis. So that means C will get rotated in the clockwise direction by 26.57 degrees. So the angle of the resulting complex number after the division will be 90 degrees minus 26.57 degrees, which should be equal to 63.43 degrees. Okay, so the multiplication and division of two complex numbers have the same effect but in opposite directions. So if multiplication scales up and rotates in the counterclockwise direction, division scales down and rotates in the clockwise direction, and vice versa. Okay, so multiplication and division of two complex numbers have the effect of scaling and rotating the first complex number by an amount equal to the magnitude and phase of the second complex number, where the magnitude gets multiplied and the angle gets added. Okay, so we have a clear understanding of the geometric interpretation of multiplying two complex numbers, and we've also seen how this is related to the matrices and vectors in linear algebra, which also produce similar kind of scaling and rotation effects when we multiply a vector with a matrix. Okay, of course, as I mentioned earlier, in the vector and matrices case, the idea can be extended to beyond the two dimensions, but the complex numbers case is restricted to the two-dimensional case only.